Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on anomaly detection using hyperspectral imaging. Let's say you are looking at a scene that consists of mostly vegetation, but you're looking for a piece of plastic or metal. In this video, I want to show you how you could do that using anomaly detection. Let's get started. As I said in today's video, I want to talk about hyperspectral imaging and anomaly detection. Traditional cameras capture 3 bands, red, green, and blue. But a hyperspectral camera captures hundreds of narrow wavelength bands, sometimes from 400 to 1000 nanometer or even into the shortwave infrared. Each pixel in a hyperspectral image isn't just a color, it's a spectrum. That means for every pixel we know how much light it reflects at each wavelength. In other words, every pixel tells a story about material composition. Because hyperspectral images capture the spectral fingerprint of materials, they're used across many applications. Some of the most prominent applications are remote sensing, medical imaging, food inspection, art conservation, and defense and surveillance. For remote sensing, they are used in satellites and drones to identify the crops, minerals, or even water quality. For medical imaging, they are used to detect oxygenation in tissues or even early signs of disease. For food inspection, they are used to detect bruises, rot, or contaminants invisible to the eye. For art conservation, they are used to uncover hidden pigments or layers in paintings. And finally, for defense and surveillance, they are used to detect camouflage or hidden objects. Each of these applications rely on one key idea: different materials reflect light differently. For example, vegetation has a strong reflectance peak around 700 to 800 nanometer. That's the near-infrared red edge. So even if two surfaces look similar in RGB, their spectra might be completely different. That's what makes hyperspectral imaging so powerful, and why we can use it to detect things that don't belong. Now imagine you're looking at a scene where most of the pixels are just soil and vegetation, but somewhere in there a piece of metal or plastic is hidden. You don't know what you're looking for, just that something might be different. That's where anomaly detection comes in. It's a blind detection method that finds spectrally unusual pixels, one that don't match the statistical pattern of the background. The most famous anomaly detector is the Xiaoli or RX algorithm. We first compute the mean, spectrum, and covariance matrix of all pixels. This would represent your background. And then for each pixel x, compute the Mahalanobis distance from the background. The larger this distance, the more that pixel differs from the global statistics, and the more likely it's an anomaly. In simple terms, the RX detector asks how far is this pixel's spectrum from what's normal in this image. Let's go to Python and see how it works. Here's the script for this video. This is where we are importing the necessary libraries, and these are some variables that we have to set, like where the data is and other things. This is where the ENVI file is going to be read. So the max sample pixels is a cap on pixels used to estimate the mean. This is to improve the speed and stabilizes the covariance. And then the reg alpha is the L2 regularization added to covariance. And then the chunk rows are the rows per block when scoring. And then anomaly percentile, which is the threshold to binarize the scores. But here it identifies the top 0.5% as anomalies. And then pseudo RGB bands is just an optional manual band indices. And then as I said, this is just to handle the ENVI file. And then the function sample pixels for stats. This function uniformly samples up to max pixel locations across the image. It would convert linear indices for efficient access. And then builds a matrix X samp of shape n by b. N is the sampled pixels, b is the number of bands. And then drop rows with non-finite values. So why do we sample here? We sample for robust covariance estimation, because real scenes often have repeated materials. A reasonable sample captures background statistics well enough. And then here is the robust mean covariance. This is where just we're gonna be computing the mean and the regularized covariance. And then this is the RX scores. This computes the RX scores in vertical blocks of the chunk rows, which is right here. And then it would also replace any non-finite entries with the feature means. This is to avoid NAND propagation. And you could see that it would also center the data. So we use the chunk because hyperspectral cubes can be very large. Chunking avoids memory spikes. And then here we also clipping the tiny negative values. we just round them off to 0. And then here is where we're going to be picking 3 bands RGB to just make a pseudo RGB image. And then here is for just normalization between 0 and 1. And then this is where the main flow is located. We open the cube and then we report R, C, and B. And then we sample up to max sample pixels. And then we estimate mu and sigma. And then invert covariance using the pseudo inverse. And then here is where we're going to be scoring all the pixels in chunks. And then we normalize them. And then here is where we're going to be thresholding at anomaly percentile. This is going to make a mask for us. And then we're going to be showing it using pseudo RGB. And then we're going to save the output as well. And here is where the results are going to be shown. Let's run it and see what happens. So it's all done. The results are saved. Let me open up the results. This is where the results are saved. So as you can see, this is the pseudo RGB image, just for the context. And this is the RX anomaly heat map, which is normalized. The bright areas here means that the pixel spectrum is very different from the background, like here. And now we're going to turn this into a binary anomaly mask. How we do it? We just do it using thresholding. Here we only keep the top 0.5% of the pixels. And that would give us a binary anomaly mask. This is the binary anomaly mask. So what are these white points? That's where something spectrally unique is hiding. Even though they look like normal pixels in RGB, their spectral fingerprints reveal otherwise, as you can see here. RX detector doesn't need prior labels or training data. It is totally unsupervised. That makes it perfect for discovering unknown materials, outliers, or even early signs of faults in manufacturing or crops. Anomaly detection is just one of many powerful tools that let us uncover the unseen. And you could also have access to the code using the link in the description section of this video. And that's about it. Thank you so much for watching this video. I hope you liked it and also found it helpful. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.